Welcome to this explainer. I am so incredibly pumped for this one, because today we're tackling one of the single most polarizing topics in the entire tech world. Look, we hear the word quantum thrown around literally everywhere, right? It's in startup pitches, blockbuster sci-fi movies, massive corporate roadmaps, but there is this massive fundamental disconnect between the shiny quantum buzzwords we hear in the media and the actual nitty-gritty microscopic physics happening in the lab. So today, we're stripping away all that noise. We're going to uncover the exact scientific bottlenecks holding us back, and we'll look at the literal blueprints for the future of computing.
Right off the bat, we have to address the elephant in the room. Is quantum computing just a massively overfunded hype train? I mean, if you're scrolling through tech forums right now, specifically there was this recent super active thread on Reddit, you'll see this exact question absolutely dominating the conversation. And honestly, it's a fair question. From the outside looking in, it feels like we've been promised a revolutionary quantum computer for a decade now, and yet we're all still typing away on standard silicon. People in the industry are actively debating whether the billions of dollars pouring into this field are actually justified, or if it's just premature commercialization pushing a fairy tale narrative. Okay, let's dive into this, because before we try to judge the future, we have to ground ourselves in reality. We already rely heavily on quantum mechanics every single day. The semiconductor is powering this smartphone in your pocket, MRI machines at the hospital, the atomic clocks that make our GPS networks function, and even lasers. They all completely depend on quantum phenomena. So the underlying physics, it's solid, it's proven. The real question we're facing isn't whether quantum mechanics is real, it's whether we can actually compute with it. But the moment we shift the conversation to quantum computing, oh boy, the gloves come completely off. Take this harsh quote from that same industry forum debate we were just talking about. Quote, "You have been duped. At this time, quantum computing has no impact on any practical problems whatsoever." Ouch. But this perfectly captures the current conflict in the industry. We have these incredible experimental machines, but right now, today, they aren't solving the global warming crisis. They aren't cracking our most secure encryption. There's this very genuine frustration from researchers who feel like marketing departments have completely overrun the actual painstaking science. Yet, right next to all that intense skepticism, you get this brilliantly optimistic counterperspective. The Wright Flyer flew 120 feet on its first powered flight in 1903. 66 years later, we landed on the moon. I love this. Another professional in the field compared our current state to the very early days of the AI winter, back in the 1970s and 80s. I mean, back then, AI was just basic Markov chains. There was no clear path to the generative AI we use today, and honestly, a lot of people called it a total dead end. Quantum computing is exactly in its Wright Flyer phase. We've proven the core concept, sure, but we are facing some truly monumental engineering challenges before we get to the moon.
Section 1. The Error Correction Hurdle.
To really grasp the scale of the roadblock here, let's look at the math from a 2026 research paper out of the University of Cambridge. Right now, our near-term quantum systems operate with an error rate of roughly 10 to the negative 3 or maybe negative 4. In plain English, that means for roughly every 1,000 operations, you get an error. Sounds okay, right? Well, not really, because to run practical applications, to hit that true quantum advantage, where these machines actually outperform classical supercomputers, we need an error rate below 10 to the negative 9. That is a gargantuan gap. It literally means our current physical qubits are far, far too noisy and delicate to do any long, complex calculations on their own.
So, the crucial point is, how on earth do we bridge that insane gap? Well, we do it by creating what's called a logical qubit. See, because individual physical qubits are so easily disrupted by things like a tiny bit of heat, stray lasers, or even just sitting there doing nothing, scientists have to use something called quantum error correction. They group dozens or even thousands of those noisy physical qubits together. Then they constantly run parity checks across them, kind of like a microscopic safety net, to detect and correct errors the millisecond they happen, ultimately creating one single, stable, logical qubit. It's a lot like twisting dozens of fragile, breakable threads together to weave one unbreakable rope.
Section 2. Building a better trap.
Think of the hardware architecture here like a ridiculously complex microscopic puzzle. In a trapped ion quantum-charged coupled device, or QCCD system for short, individual ions act as your qubits, and we hold those ions in place using electromagnetic fields called traps. We can actually move them around, split them up, merge them back together to perform calculations. Pretty sci-fi, right? Well, the massive question device architects are agonizing over right now is this:
what is the optimal trap capacity? Like, exactly how many ions should we physically pack into a single electromagnetic trap if we want to minimize our logical error rates and maximize speed? For years, the old intuition, which was even backed by previous academic studies, was that you should pack about 20 to 30 ions into a single trap. And hey, the logic totally made sense. If all your ions are sitting together in one trap, you don't have to physically move them around as much to get them to talk to each other. Makes sense, right? But then, recent Cambridge research ran the deep simulations, and the result was a massive, completely counterintuitive aha moment. The reality? A tiny trap capacity of exactly 2 ions is actually the absolute Goldilocks zone. And this brilliantly illustrates that even though you have to constantly move ions around through junctions, having only 2 ions per trap maximizes your ability to run computing dates in parallel. That drastically reduces your overall clock speed and gives you the lowest possible error rate.
Section 3. The hardware power bottleneck. Now, what's really interesting about this exact number is that it represents a shocking statistic standing squarely in our way. 780. To control the ions inside these traps, you have to use electrodes, and those electrodes are controlled by digital to analog converters, or DACs. Under the current standard architecture, every single electrode gets its own dedicated DAC. So if you want to build just one logical qubit with that required 10 to the negative 9 error rate using this direct wiring method, it's going to dissipate roughly 780 watts of power for one single logical qubit. If we eventually need hundreds or thousands of them for a truly practical quantum computer, we're suddenly looking at power requirements in the tens or hundreds of megawatts. It's wild. It's completely unsustainable. This leaves hardware engineers facing an absolutely brutal trade-off. On one hand, we have the standard architecture, which gives you direct control and incredibly fast logical clock speeds, but it practically melts down your power grid. On the other side, researchers have proposed what's known as the WISE architecture. This uses a switch-based demultiplexing network, which is a fancy way of saying it shares a smaller number of DACs across many electrodes. It solves the power scaling problem brilliantly, actually dropping the data rate and power requirements by 2 entire orders of magnitude. But the catch? Yeah, there's always a catch. You can only do one type of ion movement at a time. It restricts your computing speed so severely that complex calculations could take months or even years instead of days.
Section 4. Resolution and future outlook. But here is the good news. While the physical engineers are slugging it out in the hardware trenches, the software and algorithm side of the quantum world is racing to meet them halfway. Even as recently as winter 2025, we are seeing massive, documented breakthroughs on the algorithmic front. A recent roundup of top papers highlights some truly incredible advancements. For example, we're seeing fast quantum simulations using something called spectrum amplification, which dramatically reduces the computational cost of simulating molecules. We are seeing a massive leaps forward in QLD-PC codes, which makes all that error correction we talked about far more viable. We even have researchers creating theoretical frameworks that can handle physical qubit loss right at the logical level. The point is, the blueprint for our quantum future isn't just sitting around waiting for better hardware. The software is being actively written and optimized right now to require fewer and fewer physical resources. Which brings us right back to where we started. Yes, the hype train might be loud, maybe even a little deafening at times, but the actual science behind the scenes, it's meticulous, it's measured, and it is making undeniable progress. We know exactly what the bottlenecks are now, from insane power consumption to optimal trap capacities, and some of the absolute brightest minds on Earth are designing the blueprints to bypass them. So I leave you with this final thought to chew on. As our software gets smarter and our hardware blueprints become undeniably clear, how many years will it actually take us to traverse the gap between that very first 120-foot flight and landing on the moon? Thank you so much for joining me on this explainer. I really hope this helped bring some profound clarity to the utterly fascinating reality of quantum computing.